Ionic equations are quite similar to half equations in that both of them show just part of what's going on in a chemical reaction. So before you tackle them, I'd recommend that you make sure you're really familiar with just normal equations for chemical reactions and how they work, how we balance them. And then have a go at ionic equations. The difference between an ionic equation and a half equation is half equations will show just one ion and they're balanced out using electrons. So my example with aluminium shows just the aluminium ion and it shows it gaining electrons just to make the aluminium atom. Or chloride ions making chlorine molecules by losing electrons. Ionic equations don't show electrons, they show ions and they show more than one ion this time. I'm going to go through a couple of examples. Just as with half equations, we balance them, but the balancing is a little bit more straightforward because we don't use electrons to balance them. The first example I'm going to use is for a chemical process called dissociation, which isn't as intimidating as it sounds. Dissociation just means breaking apart. And ionic structures, as I've shown in a separate video, exist in this lattice where the ions are next to each other. But if we dissolve them in water, then the ions break apart. The lattice breaks apart so they can move around. That's called dissociation. That's what's happening to the ions. So I'm going to show that happening in an ionic equation. And the salt I'll use is magnesium chloride, which is MgCl2. So at the start, before we dissolve it, as with almost all ionic compounds, it would be a solid. And I'm going to show it breaking into its separate ions, and that's quite simple because we just need to know what the ions are, and for that we just use the periodic table. So magnesium has a charge of 2+, chloride has a charge of 1-, so that's what I'm going to show. Mg2+, and Cl-. And just to balance it, we've got one magnesium on this side, and we've got one magnesium on that side. We've got two chlorides on this side, so we need to show two chlorides on this side. I can't put a little 2 there. Remember, I'm balancing, so I'm going to put big numbers in front. So I'm going to put a big 2 there. Let's just check that the charges are balanced. No charge on this side, so overall we want no charge on this side. We've got a 2+, so we need a 2- to balance it, and we've got 2 times 1, so we've got our 2- balancing it out there. So the charge is balanced and the number of all the different atoms is balanced. I'm just going to add a state symbol. Because it's now dissolved in water, the state symbol we add is a little AQ in brackets, aqueous, dissolved in water. So that's a dissociation. We start with the ionic compound and it breaks into its different ions. That's an ionic equation because it shows the charges of the different ions. What we mostly use ionic equations for is a type of reaction called a precipitation. Again, it's got a bit of a long name, but it's fine. I'm going to use an example to show you what this is. So I'm going to start with lead nitrate. And I'm going to add to it sodium iodide. And if I added those things together, it would make sodium nitrate and lead iodide. Be a 2 there for it to balance. Now, almost all ionic compounds will dissolve in water. So these ones would be dissolved in water. And when I do this reaction, I'm just adding together 2 solutions dissolved in water and mixing it around. So at that stage, we've just got loads of different ions around because they're all separated from each other, remember. So I've got some lead ions, some nitrate ions, some sodium ions, some iodide ions, all mixed together. However, in the products, the sodium nitrate would be dissolved in the water, aqueous, but the lead iodide is an unusual ionic compound because it doesn't dissolve in water. So when that gets made, when those lead and iodide ions join together, they will make solid. And what we would see is initially we'd have a clear solution from mixing them, but as this gets formed, we see it go cloudy because we're seeing little particles of that solid lead iodide. So that's why it's called a precipitation reaction, because it makes a precipitate, the solid. So this is what we're interested in. And a typical question would ask me to show the ionic equation for this being made. Okay, so that means we're just going to finish it with the lead iodide. And this is what we're showing being made. And we just need to show the ions that make that. Okay, before we do that, let's just look at what ions we've actually got in here. So nitrate, we know, is NO3 minus. And because there's two of these, let's just show that there's two of them. If this is 1 minus and there's two of them, then the lead has a charge of 2 plus. From this one, we know that iodide has a charge of just 1 minus, and sodium has a charge of 1 plus. Again, our periodic table tells us those things. There's a big 2 in front, so I'm just going to show that there's 2 of each of those ions. So those are the ions that are in my beaker when I mix those together. Which ones am I interested in? The lead and the iodide. So I'm going to show the lead ion, which is Pb2+, and I'm going to show the iodide ion, which is I-, but there's 2 of them, so I'm going to have it balanced like that. Now, we should see that the atoms and the charges are balanced, so 1 lead, 2 iodide, 2 iodide. Charge-wise, no charge on the right-hand side, and 2 plus with 2 minus equals out to no charge on the left-hand side. So the charges are balanced out as well. If I just add the state symbols to show that at the start these ions are dissolved in the water, and at the end they make a solid. Now that is an ionic equation, and it uses just the ions we're interested in, and that means that these other ions, the nitrate and the sodium, which make the sodium nitrate, we're not interested in. And we call these spectator ions, because the sodium and the nitrate aren't involved in making the thing that we're interested in. They're not involved in making the lead iodide.